All right, almost done. Let's get through our trig section. Now, the one thing that's implied here is that you should totally know your unit circle from memory. So, 7 pi over 6 is right here, rotating that far around. And sine at that spot is the y value. Now, the y value down there has moved down, but not that much. It's going to be negative 1/2. Tangent theta is equal to negative 1. So that's saying, well, what is the theta where that's true? The theta where that's true is at, let's see here, negative pi over 4. So negative pi over 4. The answer is not 3 pi over 4. The answer is not 7 pi over 4. The answer is negative pi over 4, because the way you're going to isolate this theta is by taking tangent inverse of both sides. When tangent inverse is what you're doing to solve, tangent inverse and sine inverse are answered on the right side of the unit circle, where you answer using either anything from 0 to positive pi over 2 or 0 to negative pi over 2. In other words, here's pi over 3. You would, instead of calling this 5 pi over 3, you'd call that negative pi over 3. So you answer with the positive or negative versions of the radians in quadrant 1. So negative pi over 4, because that's where the y and x are the same. They're root 2 over 2 and root 2 over 2, but they have different signs right here at negative pi over 4 or 7 pi over 4. But again, we're only specifically using that answer. Okay, what is cosine of 5 pi over 4? Well, 5 pi over 4 is right here in quadrant 3. And the x value there is negative root 2 over 2. Now the y value there is also negative root 2 over 2. All right, cosine inverse of negative root 3 over 2. So cosine inverse, if sine and tangent inverse are on the right half, cosine inverse is on the top half, and you actually do use the radian values on the basic unit circle that you see. So we're saying, where's the x value? Negative root 3 over 2 on the top half. Cosine is x. Where is it that value? On the top half because of inverse. Now that's going to be, let's see here, right about here. That's where the x value has moved almost all the way, a far movement, 0.866 to the right instead of perfectly negative 1 to the right. And that happens at the radian, let's see here, that'd be 5 pi over 6. Last but not least, we have a composition of trig in a way. So we evaluate these from the inside out. So first the question is, what is cosine at 2 pi over 3? Let's see here, 2 pi over 3 is right there. Cosine is negative 1/2. Now this question is saying, okay, where is sine negative 1/2? Now that's on the right half. If sine's negative, we're in quadrant 4. If sine's 1/2, we haven't moved down that much. That's going to be negative pi over 6. Again, it's in the position of 11 pi over 6, but due to our inverse rules, we're going to call it the negative version of the quadrant 1 answer for sine inverse and tangent inverse. Okay, up next, using trig identities. Now, the main identities you can kind of see here are our Pythagorean identities. All right? Now there are actually probably two ways to go about this. Let's see here. Just thinking here. Yeah, I'm going to use the Pythagorean identity here because I know there's an identity that says tangent squared plus 1 equals secant squared. That's one of my 3 Pythagorean identities. Now, if I simply subtract that 1 over, then I now have an identity. I've just manipulated the identity, but I haven't changed the fact that it is an identity. I now have an identity that says, hey, if you've got secant squared minus 1, that's equivalent to tangent squared. So I'm going to use that now. If secant squared minus 1 by my identity is equivalent to tangent squared, then why don't I just write tangent squared? Now I've got tangent squared over tangent squared, so this whole thing is just equal to 1. So why write all that ugly mess if you can just write 1? All right. Up next, still using our Pythagorean identities, I've got an identity that says sine squared plus cosine squared is equal to 1. Now you might be thinking that you're going to be manipulating the numerator because you've got a 1 and a sine, but the numerator doesn't have squared trig. The denominator has squared trig. We're actually working with the denominator. So same idea. If I move that over, I'm just going to do that in my head. I'm going to now be able to say cosine squared theta is equivalent to 1 minus sine squared theta. Now, 1 minus sine squared is a difference of squares. We factored those before. A difference of squares factors to, well, 1 roots to 1 and 1. Sine squared roots to sine and sine. Square roots to sine and sine. Difference of squares, square roots. And we just write each factor with a different sign. Difference of squares. 1's a square. Sine is literally squared. So we can write those root of values. So we get some canceling here. That whole root cancels out with that. So this is equal to 1 over 1 plus sine. That would be the simplified version. Doesn't look that much simpler, but at least now having two different trig values and some squareds, we only have a single fraction with one trig value. So that is, in some ways, more simple. All right, prove that this identity is true by manipulating the left-hand side. All right, the way we do this, and I guess I will be nice and tell you, this problem right here is actually not necessarily going to help you in Calculus AB, but I still want you to have the understanding of how these identities work. So just know that, if this is the one that for some reason makes you say, I don't know if calculus is for me, it is. You won't interact with this much, but you still should have some idea of how to navigate it. So I've got my left-hand side, and what I'm going to do is, since I've got two fractions who are adding to one another, if we really pull back the layers here, ignore the trig, what's going on here? Addition. And what are we adding? Fractions. And then what are those fractions composed of? Trig. Well, if I'm adding fractions, no matter whether there's trig or numbers or anything, I need a common denominator. So what I'm going to do with the left-hand fraction is multiply by cosine over cosine. Multiply by 1. Multiplying by 1 is not changing the value, but it's changing how it looks. It's giving me that common denominator. Same here. I'm going to multiply by 1 plus sine on this side. Now, why am I multiplying by 1 plus sine over here and cosine over here? Because I'm multiplying the other denominator by what it has. Because now when I read this denominator, I see cosine times 1 plus sine. When I read this denominator, I have cosine times 1 plus sine. Well, those are the same or common denominator. So what happens now? Up here we get cosine squared. And I'm going to write it like this. I'm going to do some work ahead here. I'm going to FOIL out this. That's going to FOIL to 1 sine, so I've got two sines, and sine squared. On the bottom, I'm going to leave that unfoiled. And let's think about what I'm trying to get here for a second. I'm trying to get to 2 secant. All right. Well, I see a 2. Okay. And I need secant. So here's what's going on the grand scheme of things. Somehow, I need this 1 plus sine to go away because secant is really cosine on the bottom. So what I know is somehow 1 plus sine is going away, and I'm only going to have a cosine on the bottom. Now that doesn't necessarily help, but just think about that. What is my goal? What am I trying to get? I'm trying to get 2 over cosine. Somehow I need everything else to go away except for 2 and a cosine. So how am I going to do that? Well, first I'm going to notice that I've got cosine squared plus sine squared. And right back up here, that identity says if you've got a sine squared and a cosine squared, you can replace all that. We could regroup that and move it over, but essentially that's all going to turn into just a 1. So sine squared and cosine squared have become 1 by my identity. I've now got 1, a 2 sine, and a 1. So what I really have is I've got 2 plus 2 sine over cosine times 1 plus sine. I'm going to go ahead and factor that 2 out because that is the magic of this problem. Now I've got essentially my answer already. My 1 plus sines are going to cancel, and I now have 2 over cosine, which, hey, did you know that that's 2 secant? Yes, it is. All right. And now we've got our last section. Let's see if I can do this somewhat quick. Let's see here. Given that sine is root 3 over 2, determine the values of cosine, tangent, and secant. All right, well, I've got that sine is 3 over 2, and that my theta is, that's a fancy way of saying quadrant 3. Let's draw that out. If I'm quadrant 3 and my sine, whoops, that should be negative root 3 over 2. I made a typo. Oh, never mind. That's quadrant 2. Quadrant 2. All right, there's pi over 2, there's pi. So I'm in quadrant 2. Sine is root 3 over 2, that's right there. Where is that? Well, I know where that is. That's 2 pi over 3. That's my radian. Now, what are the points there at the end of that? That's negative 1/2 root 3 over 2. So now I know everything about this theta. This theta belongs to, this section on the unit circle. Now, what's cosine? Well, I kind of already wrote it down. Cosine is the x value at that spot. So this is saying find where you are. There I am. I'm at 2 pi over 3. Now that you know where you are, what's cosine at 2 pi over 3? Well, negative 1/2. What's tangent? Well, tangent is the division of the y coordinate, or sine, over cosine. That's what tangent is. Sine divided by cosine, or the y value divided by the x value, because y is sine and cosine's x. When we divide fractions, we keep, change, and flip. Or we multiply by the reciprocal. It's the fancier way of saying that. The 2's will cancel, and I'm just going to have a negative root 3. And now the question is, what's secant? Well, secant is just cosine flipped. Well, I found cosine up above, so it's just negative 2. Now I've got negative 2 over 1. Or really, secant is the reciprocal of cosine, to say that with some better math language. Okay, almost done. It's now time for dealing with exponentials and logarithms. So, let's see here. This one, again, I've got a base, I've got an exponent, and I've got an answer. I'm going to rewrite as the log of the base gives me the exponent. A log of the base to that answer on the other side gives me the exponent. We're just simply rewriting, and that is the answer. Now you can plug that into the calculator and figure out what that is. It's going to be some very ugly decimal, but really, you solved for x. You don't have to figure out what that equals per se. All right, up next with the same idea. E is our base, that is my exponent, and that is my answer. So we really have a, whoops, I don't have a log, I have a natural log, because E is my base. So I don't have to write the E on the bottom, it's implied, but the natural log of 5 will be equal to that exponent. Now I just need to simply get x by itself, so that's x equals ln 5 divided by 0.65. Now another way of writing that, typically we don't like writing fractions with decimals because a decimal is really a fraction. We don't like nested fractions or fractions and decimals mixing. So what could we do to fix that? We could take a step back and say ln 5 is really, let's see here, 0.65. If you got a 65 on a test, hopefully you didn't, then you got 13 out of 20 correct. Or really, you could just write that as 65 over 100 and reduce the 5. Because again, this decimal is 2 places. It's in the hundredths place. So this is really 65 over 100, which reduces to 13 over 20. So now if I want to get x by itself, this really, I'd multiply by the reciprocal and get 20 over 13 ln 5. It's the better way of writing that, but that is technically correct. All right, last but not least, we got to do this one more time. Now I'm starting with a logarithm. So the way I'm going to get that x free is by turning this into its exponential form. So 2 is the base, 64 is the exponent, a logarithm equals the exponent. It's equal to x minus 3. And all I have to do now is add 3. Now don't try to plug that into the calculator. You'll get something like overflow because that is a giant number, but those are your solutions. And now we are done with the whole summer assignment. You did it.